Dear students, welcome to the last discussion with respect to Module 1 where we talked about fundamentals of logic. The last topic discusses on proof of methods. As the name says, proof of methods, we have a set of methods, around 3 methods in this syllabus. Actually, there are 5 to 6 methods, but we will be considering 3 of them, which deal with how given a conditional we can prove with along with the quantifiers whether the statement is true or false. So here basically we consider most of the propositions coming from the mathematical discussions involving conditionals or implications. So we'll have a setup like this, that is P implies Q, and we'll be considering such implications or conditionals as a part of our discussion under the proof of methods. So here let P and Q are the simple or maybe a compound propositions. There may be compound propositions as we discussed using your all conjunction, disjunction and stuff like that, and which in turn may involve quantifiers. So here not only conditional, here we are also having quantifiers attached to them. So given a conditional of this form along with the quantifiers, how we can prove? So to prove them, as we discussed, we have 3 methods what we are going to use here, and using any of them or a couple of them or all of them, how we can prove whether the given statement is valid or invalid or true or false. So given such a conditional, so coming to the definition of a proof of method, given a conditional of P to Q form, the process of establishing the conditional is true. The conditional is true by using certain rules of logic or some inferences is going to be called as a proof of the conditional. The proof of the conditional can be identified in several ways, and those can be identified as a direct proof, indirect proof, proof of contradiction or proof by contradiction. So direct proof, as the name says, we can directly establish using all our laws of logic or maybe some of the inferences or rules of inference. All those things can be directly used and prove. That is going to be a straightforward method. Indirect proof, where we are going to use the contrapositive of the given statement and start using that and prove the result is true. Then third is contradiction. So assume the given statement is false. Even though it is true, assume it is false. Then go back to the conclusion that whatever we assumed is not matching in line with the whatever the rules of inference or laws of logic is there, and thereby we prove that whatever we assumed is contradicting the conclusion or the inference. Thereby we establish proof by contradiction. So going back to telling that the statement is true. So there are 3 different ways which finally give us whether the given statement or conditional is valid or not. So let us find the step-by-step process for each of them. So to start with, direct proof. The direct proof of a conditional involves the following lines of argument. So conditional we are taking, which is a P implies Q. So assume the P is true, is a straightforward method, assume it is true. So using all our possible laws what you have seen so far, prove the Q is also true. When we can establish P is true and Q is also true, probably we can say P implies Q is going to be true as per the truth table. Next, indirect proof. So we have a conditional P implies Q. So we also know that the contrapositive of P implies Q is nothing but negation Q implies negation P. Both are logically equivalent. So once we are given with P implies Q, let us take the contrapositive of it and prove that this is going to be true. When we can prove negation Q implies negation P is true, probably we can say, or we can imply rather logically, P implies Q is also true. That is the indirect method of providing the solution for the given conditional. And the last one, so assume P implies Q is a false. So whatever the given statement we have, we assume it is going to be false. Then by using all those rules of reference, rules of inference and logic, we find that once P is false, then Q is also false, or once P is true, Q is also true. All those things can be taken from the truth table. So in order to P implies Q to be false, we should have either P is true, Q is false. That is only possible as per the truth table. So we are assuming now P is false. So when P is false, Q should be true. Then by we will be getting true as the solution. So like that we start considering the given statement as a false, somehow to make sure that whatever we have considered is not valid, probably we infer that P is going to be false. So that which is going to contradict that P is going to true. So we have taken P implies Q is false, where we assumed P is true, and while inferring we are telling P is false. So we assume P is true, we are telling somewhere P is false, which is contradicting to each other. Thereby we use the proof of contradiction and make sure that P implies Q is a true value. Probably it is a confusing statement at this point of time. Probably when you take some examples, it will be clear to you. So what we have to say here is there are three methods: direct method, or direct proof, indirect proof, and proof by contradiction. So direct proof, as the name says, we assume the given statement is true, that is P is true out of P implies Q. So next we prove that Q is also true. When both P and Q are true, we can infer that P implies Q is true. The second one, indirect proof, will not directly prove P implies Q is true, but we will take the contrapositive of it, because we know that P implies Q is logically equivalent to negation Q implies negation P. So we'll take negation Q implies negation P. We prove that that is true. Thereby we imply that P implies Q is true. Next, third one is contradiction, proof by contradiction. We take P implies Q as false, and in that the possibility for this to happen is P is true and Q is false. Using our laws of logic, we infer that P is false. We are assuming P is true, we are inferring P is false, which are contradicting to each other. Thereby we say that what we assumed is not correct. Since what we assumed is not correct, or what we have proven is not correct, thereby there is a contradiction, and we show that P implies Q is true. So let us go into some of the examples where we can clear any doubts what we might be having out of this. So first one, so let us prove for all x, P of x implies logically there exists x, P of x. Similarly, for all x, P of x or x implies there exists for all x, P of x, or there exists Q of x. Just we are asked to prove. That means there is some x where the P of x is going to be true for all those x. From that, we are taking a subset where there exists P of x. By looking at this itself, we can say it is possible. That means we have a superset, and in that superset we are telling prove subset is true. Obviously, subset is a part of the superset. Thereby, we can say that is possible. Similarly, here we have two sets here which belong to the superset, and we are telling to prove one belongs to the superset, other belongs to the subset of the superset, which both are again possible. We can prove. So let us see mathematically how we can prove them. So assume S is the universe, because for any inference to draw we should have a universe. So let us assume S as universe. So let us consider the given statement for all x, P of x. That implies P of x is true for every x belongs to S. That is the meaning of this for all x, P of x. So P of x is going to be true for every x that is belonging to S. So when P of x is true for every x belonging to S, can I say for some A or for all A, that is x is having that value A, I can say P of A is also true. So I am just replacing x by A, because x can be any value that is belonging to S, and I give some value for x, say A, and if that is true, then P of A should be true. When P of A is true for some x of A belonging to S, I can say P of x is true for some x belonging to A. For all S it is true, then I can say for some x is also it is true. When it is true for some x, probably I can represent mathematically as there exists P of x. That's what we have proved now. For all x, P of x implies there exists P of x. It's a common sense which is going to be shown here through mathematically. Similarly, the next one is same as the above. So for all x, P of x or Q of x, so we can distribute that using P of x or Q of x is true for all or every x. Next, P of x is true for every x, or Q of x is true for every. I am just applying the disjunction whatever we have as per the set theory or laws of logic is concerned. So when I say P of x is true for every x, like we did in the previous one. So for all x, P of x or Q of A is true for A of A belongs to S. If that is the case, I can say for all x, p of x is true, because I need not worry about this because I am supposed to prove the same as it is. So let us not disturb this. Only here we have to see. So this is based on the previous problem what you have taken. We have proved there that for all p of x, we have a x belonging x is equal to a is true. Similarly here, for all q of x, I can say q of a is true for a belonging to s. Just we did in the previous problem, same we are copying here or using otherwise. So when I say this is true, I can say that there exists x for which q of x is true. So which we have proved now. So for all x, p of x or q of x, I can logically imply or infer that for all x, p of x or there exists x, q of x. So this is again a sense of common mathematical relation which we have proved again using these symbols. Okay, just straightforward one, but just to understand how this is going to be used using our proof of methods. So let us take the second problem, and this problem was asked in the examination. So here what we have to say is, please understand the problem as a mathematical one. Don't give any meaning for this. If you start giving meaning, then you will not be able to get the solution. Just use it as the statement as given here. Okay, give a direct proof of the statement. They are asking to prove a direct proof for the given. What is the statement? The square of an odd integer is an odd integer. Take the statement as it is, we will see. So the square of an odd integer is an odd integer. So this is a statement, but we are supposed to use direct proof. As we discussed just now, this proof, either direct proof, indirect proof, proof by contradiction, is applied for a conditional statement. First see whether the given statement is in the conditional form. If it is, fine. If it is not, we have to convert that suitably into conditional form. Conditional form means if, then. So for the given statement, since it is not in the conditional form, we will identify its associated conditional. So the square of an odd integer is an odd integer. So if you put in conditional, if I have a n which is an odd integer, n square is also going to be odd integer. I am just writing in the conditional form like this. If n is an odd integer, then n square is an odd integer. So if is going to be the starting point of conditional, it contains n. So these two we have added in between, otherwise the meaning same. So n is an odd integer, n square is an odd integer. Okay. Now, having said that, we have a 3-step process to follow. So step 1, assume now we have the value that is n is an odd integer. So n is an odd integer. So mathematically we all know from high school, odd integer is 1 which is 1 above the even number or vice versa. Or when I divide a given number, you always get some remainder. If that is the case, probably we can say the given integer is going to be an odd integer. That's how we compare an odd and even. So mathematically, n is equal to 2k plus 1 is the definition what we can consider for a odd integer. So where for some integer k, we can have this relation being true. So if I say 5, how I can write 5? 5 is equal to 2 into 2 plus 1. So 2 into 2 is a 4 plus 1. So some integer I can establish 5. Similarly 7. 7 is an odd integer. I can write 2 into 3 plus 1. So for some value of k, I can represent the given odd number as a n is equal to 2k plus 1. So now this is the p. Now what is q? Q is nothing but n square is an odd integer. So let us take what is n square. So we know what is n here. So n square will be here as per this 2k plus 1 whole square. So mathematically this is the equation what you will get in two terms, that is 4k square plus 4k plus 1. If you look at this 4k square plus 4k is something which I can take 2 as a common factor, or maybe 2k to some extent. If I take that, I will get some form of the n is equal to 2k plus 1. So something after this we have a plus 1. So we know that 4 is a even number, another 4 is even number. So k square, you take any number that is going to be squared, maybe a positive, so maybe an odd number or a even number, that has to be considered as a odd number. For example, 3 square is 9. So if I have a k as odd number, I will get a odd number as a square. If I have an even number, I will get even number as a square. So whatever it is, I will get some number. So this is going to be some number plus 1. So any number plus 1, we know just now we have seen, is going to yield a base number only. So if you divide that by 2, so probably you will get a non-zero number, which is nothing but a odd number. So even number will never get a remainder. Remainder is always 0. A valid even number will always get a 0 as a remainder, whereas a base number or odd number will get something that may be 1 or 2 or some number beyond 0, non-zero will be yielded. So if that is the case, I can conclude that whatever n square here we got, that is 4k square plus 4k plus 1, is going to be a odd number always. So as per the definition of an odd integer, we get a remainder as non-zero when an odd integer is divided by 2. So if this is the odd integer, if at all, when I divide it by 2, I will always get a odd integer. So 4k square plus 4k plus 1, because of this extra plus 1, will always give us the remainder when we divide by 2. So when some number is giving remainder, means it is not even. If it is not even, what it should be? It should be an odd number. So what is the conclusion now? Since it is not divisible by 2 completely, so we say n square is a odd number. So we assumed n is an odd number, and we have proved n square is an odd integer. Thereby the given statement, if n is an odd integer, n square is also an odd integer, is valid or true. This is how we have proved. So what the method we have followed here? A direct proof. In the direct proof, we assume, as the name says, what is the P implies Q. We assume P is true. We infer that Q is also true. When P is true, Q is true. Obviously, as per the truth table, P implies Q is also true. So that's what we have proved. Take another example. Again, direct proof. Show the square of an even integer is even integer. In the previous problem we have taken, the square of an odd integer is a odd integer. Now we are taking square of a even integer as a even integer. Same process. First check whether the given statement is in the conditional form. If it is not in the conditional form, we have to convert into conditional form. So again, if, then. So if n is an even integer, n square also will be even integer. So step 1, assume n is an even integer. So an even integer is like this. For odd integer there will be plus 1. For even integer, plus 1 will not be there. This is even. You take any value of k. 2 into 0 is 0. 2 into 1 is 2. 2 into 100 is 200. 2 into 21 is 42. You take odd or even, you will get always a even number when you multiply with a even number. So this is the definition for a even number or even integer. Now, since we have assumed n is a even integer, let us see what is n square. So n square we are getting 2k whole square, that is equal to 4k square, that is nothing but 4 into k square. Again, let the any value of k, let it be odd or even. When I multiply a number or integer with an even integer, you will always get an even integer only as per the mathematics. So we are getting 4k square being always a even integer. That is the conclusion. So that is the inference. Based on that inference, what is the conclusion? Since 4k square always gives us an even integer, so which is 4k square in our case? That is nothing but n square. So n square also will be an even integer always. So what is the final conclusion now? If n is an even integer, then n square also will be a even integer. So we have proved using direct proof. Now let us take direct proof and indirect proof for the given statement. If n is an odd integer, then n plus 1 is a even integer. So they have given already in the conditional form. You need not convert, it is already given. So what is the conditional? If n is an odd integer, then n plus 1 is going to be a even integer. So first, assume n is an odd integer. Just now we have seen, if it is odd integer, the definition is going to be n is equal to 2k plus 1. So now let us assume n is an odd integer and n plus 11 is going to be what? So n plus 11 is going to be, n is nothing but 2k plus 1 plus 11, that is equal to 2k plus 12. If you take the common factor 2, you will get k plus 6. So let any number k plus 6 can be any number. When I multiply with 2, it will always give even integer because 2 is a even number. It doesn't matter what is the other factor, you will always get the even number. So the inference is 2k plus 12 or 2 into k plus 6, which is nothing but n plus 11 in our case, is always going to give us a even integer when n is the odd integer. So conclusion is, since n plus 11 gives us always a even integer, we can say that if n is an odd integer, then n plus 1 is going to be a even integer. So next problem. Sorry, the same problem we are going to prove using indirect proof. So indirect proof, direct proof means we'll take P, we'll take Q, we infer P implies Q based on P is true, Q is true. Indirect means we'll take the contrapositive of it, then we'll start proving. So what is the contrapositive of P implies Q? It is negation Q implies negation P. So we have taken the contrapositive of P implies Q as negation Q implies negation P. So what is the step 1? First assume what is the integer, whether integer is a even integer or a odd integer. So what is P? We have to take the contrapositive, negation Q of x implies negation Q of x. So P of x. So we assume now P of x is going to be, n is an odd integer, Q of x is a, n plus 11 is a even integer, same P, Q, there is no change. Since negation Q implies negation P is what we have to prove, so first step is, what is negation Q? So Q is n plus 1 is an even integer, negation will be n plus 1 is a not an even integer, that means odd integer. So when n plus 1 is not an even integer, then probably it will be odd integer. Since it is odd integer, the definition is going to be 2k plus 1. So n plus 1 is equal to 2k plus 1 is what we have got as per the contrapositive nature of the given statement. Now, when we know what is n, then we have to say what is n plus 11. So n plus 11 is going to be 2k plus 1 plus 11. So n is equal to, one second. So n plus 11 is equal to 2k plus 1, that's what you have taken now. So when n plus 11 is 2k plus 1, we have to go back to the other side, that is what is n. So if you using the same way, so n is equal to 2k plus 1 minus 11, that is equal to 2k minus 10, which is going to give us 2 multiplied by k minus 5. So we got reverse case. We already got n plus 1 is not even, that is a base, that is odd number. We'll go with what is n, that is what it is, negation Q and negation P. So when I multiply any number with the even number, I will always get even number. The result is going to be even number. So when n is an even number, that's what, when n is a even number, so and we have shown that n is, one second. So here we have got that n is equal to a even number. So n is going to be a even number. Hence n is going to be an even integer, as such n is not odd. So what you assume now? We have assumed n plus 1 is not even, that is n plus 11 is a odd number. Then we are proving that n is also odd number. When n plus 11 is also not even, that is odd. When n is also not even, that is not odd, that is even, then we prove that the contrapositive of the given statement is true. What is the contrapositive? For if n is equal to, if n is an odd number, if you look at the statement, if n is an odd number, odd integer rather, we will get n plus 11 as a even integer. What is the contrapositive of this? If n plus 11 is not an even integer, if n plus 11 is not an even integer, then n is also not an odd integer. Have you proved that? Yes. If n plus 11 is not an even integer, then n is not an odd integer. That's what we have proved. Since we have proved the contrapositive to be true, I can say that since logically it implies to P implies Q, I can get to the main statement, that is, if n is a odd number, if n is a odd number, probably n plus 11 is a even integer. So we could prove the statement as true using the contrapositive method, which is nothing but proof by indirect way. So indirect method of proving the statement. So this is how we could do. So next one, I think contradiction which you could not see. Let us have an example. Prove the following statement using contradiction method. So what is the statement? If n is an odd integer, then n plus 11 is even. Just now we have done in different methods. Let us use contradiction also to prove the same statement is true or false. So check whether the given statement is in conditional. Yes, it is in conditional form. Let us not convert it again. So it is already there in the conditional form. So as per the contradiction, we have to assume the given statement is false. That is a contradiction. Okay. So false. That means assume that n is an odd and n plus 11 is a odd. So what is the statement? N is an odd integer, then n plus 11 is a even integer. So what I am going to take? I am going to assume P implies Q is a false. When it is possible? When it is P is true and Q is false. So I am assuming now n is odd, but I am taking n plus 11 is also odd. Okay, I know it is not correct, thereby I will prove by contradiction. So one statement I am taking as a false statement, thereby P implies Q becomes false. So to make P implies Q to be false, P should be true, Q should be false. So n is an odd is a true value, n plus 11 is even actually, but I am taking it as a odd. So that is nothing but false. So I will take this and I will prove it is contradicting. Now since n plus 11 is a odd, I can say n plus 11 is equal to 2k plus 1. It's actually n plus 11, sorry, small correction, n plus 11. So n plus 11 is equal to 2k plus 1. Why 2k plus 1? Since it is odd number mathematically can be written as 2k plus 1. Now with this, n is equal to 2k plus 1 minus 11. Sorry, small correction. Make it minus 11. What is minus 11? Here minus 11 plus 1, 10. So this becomes 2 into k minus 5. Make small corrections here, just mathematics. 2 into k minus 5. So any number that is multiplied with an even number such as 2 will always results in even number. We have been looking that for several problems so far. So when I am multiplying k minus 5 with 2, irrespective of what the value of k, I will always get a even integer, maybe a z plus or z minus, whatever it is, I will be getting even 2, 4, 6, 8, stuff like that. So I am assuming now n is a odd integer, but what I am proving now, n is a even integer. So what I assumed is a odd, what I am proving is a even. So I am contradicting now my assumption which I have taken as a n is a odd. So contradiction is considered here, meaning that my contradiction of n is an odd integer is not valid. So thereby I say that this particular inference, that when I take n as a even integer, I cannot have a n plus 11 as a even integer. It should be other way. So when n is an odd, then only n plus 11 is going to be odd integer. So whatever my assumption is going to be false. So what is the assumption now? N plus 11 is a odd integer. No, it is going to be even. So I can prove now with the contradiction n plus 11 is a even integer. That is what it is now. So what we assumed here now, n plus 11 is going to be odd, but now we have proved contradiction. So what is the contradiction now? N is taken as odd, but n is proved as even. Thereby, whatever we assumed is not going to be true. What we have assumed now, n plus 11 as a odd. So when n plus 11 is odd, that is what false here, no? So when n plus 11 is odd is not considered in the inference, it should be otherwise, meaning that that is a false statement. So what is the true form of it? N plus 11 is going to be a even integer. So n plus 11 is even, that's what we have proved. So when n is an odd integer, n plus 11 is even. So contradiction normally is slightly confusing because we take a totally negative approach and come back and prove that that negative approach is negative, thereby negative into negative is going to be positive. So I advise you to go through again or take a couple of problems on this nature, so that you will have a comfort in identifying how contradiction can be used as a proof. Okay, so finally the method behind contradiction is, take this statement, we know it is a conditional always will have a truth table. You know that TT is T, TF is false, FT is true, and FF is true. Remember that. And consider conditional is false. So when conditional is going to false, when P is true and F is false. So accordingly, assume that, prove that what you have assumed as a true is contradicting with what you have got in step 2. When that is the case, probably what you have assumed, that is the false statement, is not correct. So when false statement is not correct means false statement is going to be reversed now, negation of it. So n plus 1 is going to be even is valid now. So that is how it is called as a contradiction. So probably let us take one more problem and see how we can consider this. So give a direct proof of the statement, sum of two even integers is itself an even integer. So again, conditional concept is missing. So we can make, if m and n are two even integers, then m plus n is an even integer. So whatever the statement we have got, we have converted that into a conditional form. So here step 1, m and n are even integers. So when I say even integer, you have just now seen even integer will not have plus 1, it is only odd integer. So I take m is equal to 2a, n is equal to 2b for some value of a and b. We know that when I multiply any number with a even number, I will always get a even number. So this is a correct definition for even number. This is also a correct definition for a even number. So now step 2, m plus n. So that is 2a plus 2b, which is nothing but 2 of a plus b. Again, by applying the definition of an even number, when I multiply a number with 2, I will always get a even number, because 2 is a even number. So with that, I can say that 2 into a plus b is a even integer. So we assumed, we considered m and n are going to be even integers, and we have proved now m plus n is also a even integer, because m plus n is nothing but 2 into a plus b, where 2 into a plus b is a even integer. Thereby we can say the given statement is going to be true. That means when m and n are even integers, m plus n is also a even integer. Okay, next one. Show that the premises. This is just asked, I am just sharing for your understanding. So a particular problem of this nature also is possible to be asked in the examination. A student in this class has not read the book. That is the statement actually. A student in this class has not read the book. Next, everyone in this class passed the first exam. He is asking whether we can imply this conclusion with this: someone who passed the first exam has not read the book. This is the statement given. That's what I said in the beginning. Don't give any meaning for this statement, but take the statement as it is. So what is the statement? A student is a part of a class. He or she has not read the book. There are two statements actually here. A student is in class and has not read the book, because in a class there might be 100 students. All might not be reading, some might read, some might not be reading. So a class is a different, student not reading book is a different. Then everyone in this class passed the first exam. So each of the student in the class passed the first exam. Whether it can imply to the statement called someone who passed the first exam has not read the book. So maybe confusing to start with, read couple of times, probably you'll be able to get, but split this given statement into individual premises or statements, probably will get a clarity. So let me consider C of x, C for class, B for book, and P for passing the exam. So C of x is in the class, some student is in the class, and some student who is in the class has read the book. Then some students who is part of the class has passed the first exam. So your entire given premise cannot go beyond these three statements. X should be class, X has read the book or not read the book, he or she are passed the exam or has not passed the exam. So beyond these three will not be able to go. So based on the given statements, let us represent them in logical form. For some X, a student in this class has not read the book. and everyone in this class passed the first exam. These are the two opening premises for us. So a student in this class has not read. A student means someone, not all. A student, 1 out of 100. If one student has not read the book, probably we take that as a statement. So there exists a student who is in the class but has not read the book. That is represented as there exists x, comma, c of x, part of the class, and is in the class but he has not read the book. So negation of b of x. Next one. Everyone in this class passed the first exam. Everyone in this class passed the first exam. So everyone means for all x. For all x, c of x, they should be in the class and passed the examination. So everyone in this class has passed the examination. So passed means since you are part of the class implies that you have passed the examination. So c of x implies p of x. Now with this, can I conclude? What is the conclusion? Conclusion is someone who passed. Someone means there exists x. Someone who passed the first exam. So who passed the first exam means p of x has not read the book. So has not read the book, negation of b of x. So it should be and symbol. So it should be, both should be true. Okay, let us take the first statement, what we can infer. So there exists x, c of x and negation of b of x. So we have to show whether this statement is a true or not. What is the statement? There exists x, p of x and negation of b of x is true or false. If it is true, we can say the given statement is valid. If it is not true, we say the given statement is not valid. That is going to be the case what we are going to consider now. C of x true, assume now for some x. Negation b of x is true for some x because we have used conjunction. When conjunction will be true? When both the premises are true. So as per this, c of x is also true. Negation of b of x is true. When negation of b of x is true, b of x is going to be false. Second statement. For all x, c of x implies p of x. So c of x implies p of x is going to be true only when c of x is true and p of x is going to be true, or c of x is false, p of x is false, and stuff like that. So p of x should be true because c of x is already true. Since c of x is already true, p of x should be true because when both true only, probably I will get this implication as true. So thereby c of x, p of x is going to be true for p of x being the true value. So we got this now. So this is for there exists. That is the first one. Second one is for all x. Next, what we have to infer now? For some x, can we have p of x and negation of b of x as a true or false, whatever it is. Let us see what we are going to get now. So we know that from 1 and 2, p of x is true for all x. P of x is true for all x. Negation of b of x is true. Negation of b of x is true for some x. For some x. Now, can I say that p of x is true for some x? When p of x is true for all x, can p of x be true for some x? Definitely, common sense. So, this is true. And we know that negation of b of x is true for sum of x. When this is true for sum of x, I can infer that for some x, p of x and negation b of x is true. Thereby, the given conclusion is valid. So this is how we have proved that the given statements are valid. So in the exam, you might get questions of this category, but don't be worried. First, try to represent them. I have not done anything different here. I have just taken the statement as it is. A student in the class has not read the book. So when I say a student has not read the book, can I say the student is outside the class? No, because the statement says a student should be in the class first, then only I am talking whether he or she has read the book or not. So it is a conjunction. Then second one, everyone in this class passed the first exam. So everyone in this class, since you belong to this class, you have passed the exam. So that is implication. Okay, there I cannot say conjunction because you should be in the class. You should be in the class, but we have to pass the first exam. Only being a part of the class, we have got the eligibility to pass the exam. So that is the implication we are getting here. So thereby that is going to be a implication or a conditional. So that's how it is represented as a conditional statement. Okay. Now, so some of the examples I have listed for you so that you can take them as an exercise and identify. But whatever it is, the three methods, direct proof, indirect proof, proof by contradiction, are very important from exam point of view, and you will be getting at least one of them for 6 to 7 marks. The concept is very easy. Only thing is have some patience to understand which method is asked, because there are chances here you get confused. So direct proof means, as the name says, consider P implies Q, assume P is true, prove Q is true, confer or conclude P implies Q is true. Indirect proof, take the contrapositive, as the name says indirect, we are proving P implies Q from the different form, that is the indirect method, indirect way. So indirect way for P implies Q is only possible is through contrapositive, that is negation Q implies negation P. If you can prove that, I can say since both of them are logically equivalent, P implies Q is also valid or true. And third one is the contradiction. So P implies Q is false, assume that as a false, that is a contradiction. So when P implies Q will be false, when P is true and Q is false. So thereby you are taking Q as a false in the contradiction. So by taking Q as a false, somewhere you come in the middle step, we say that whatever you assume that Q is false is going to be not valid and it is contradicting. When I say something is contradicting, your assumption is not correct. So what is the assumption? Q is false. So when you have taken Q is false and it is contradicting, what is the inference? Q is true. So that by we say that P implies Q is a true. So that's how we have to identify the proof by contradiction. So with this we are concluding the module 1. So hope in a long, probably a long module we had in this with the different subsets and different concepts as well. So, and this is very important. So probably you will have your third test based on this. Okay. So we conclude module 1 now. Next we will start the final module, module 3 soon. Thank you.